Hello, and welcome to our lecture on matter and minerals. Just get the slideshow going here. Okay, so today we're talking about the basic building blocks of matter, atoms, and minerals. First, we'll start with atoms, what they are, and how do they interact with one another. So an atom, for those of you who are not familiar, is the smallest, most fundamental unit of any element. And they themselves contain smaller pieces or particles, which include protons, neutrons, and electrons. So in the center of the atom, it's called the nucleus, is the protons and neutrons. Protons have a positive electrical charge, and neutrons have no electrical charge. And surrounding the nucleus are electrons, which have a negative electrical charge. So as I mentioned, the positively charged protons and neutrally charged neutrons are located in the center of the atom, known as the nucleus, and the electrons orbit the nucleus. So the negative electrical charge of the electron is attracted to the positive electrical charges of the protons in the nucleus. So a chemical element is one of many substances found in nature that cannot be chemically broken down into any simpler substances and maintain the same characteristics. And these chemical elements, they are basically the primary constituent of matter. And each element is unique in the number of protons that it has inside of its nucleus. So, for example, gold is a chemical element. So you could break a piece of gold down into many different pieces, and those pieces would still be gold. The smallest piece of gold you can have and have it still be gold would be one atom of gold. And so that's what makes it a gold a chemical element. It's the basic constituent of matter. So if you would break that atom down any more, it wouldn't be gold. It would be some other material. And here is a periodic table of the elements. You see each element has a symbol. Okay, so this one is hydrogen, symbol H, and the number above the symbol is the atomic number. That is the number of protons in the nucleus. And you'll notice that each element has a unique atomic number. Okay. So these electrons in the atom, they orbit the nucleus, and they live in these things or reside in these things called principal shells. Okay, so you can think of these principal shells as regions surrounding the nucleus of the atom. And each shell contains different electron orbitals, which can contain only a certain number of electrons. So these electron orbitals are kind of like rooms within these shells that electrons can reside in. So the analogy I like to use is an apartment building. So each shell is a floor of the apartment building, and each orbital is a room on each floor of the apartment building. And so there's different types of electron orbitals, and I like to call the orbitals kind of like apartments. So there's different apartment units. There are s orbitals, which can contain up to 2 electrons. So this is one type of apartment unit, an s orbital, where it has 2 bedrooms. So each person lives in one bedroom. So each electron is in one bedroom. So an s orbital can only hold up to 2 electrons because it only has 2 orbitals. Two electrons. So, and p orbitals, you can think of these as apartment units that have 6 bedrooms. So they can hold up to 6 electrons. And so remember, these principal shells are like floors in the apartment building, and the floors contain different apartment units. And those units can be either s orbitals or p orbitals. And the 2 different types of orbitals have different, or apartment units, using analogy, have a different number of bedrooms and can hold a different number of electrons. S orbitals holding up to 2, p orbitals holding up to 6. So the first electron shell, or you can think of as the first floor of the apartment building, has only one apartment unit, or one orbital, and that's an s orbital. So it has two bedrooms in it, and so only up to 2 electrons can exist in that first shell. The second electron shell contains an s orbital called the 2s orbital and a p orbital called the 2p orbital. And so this is like the second floor of the apartment building, and it has two apartments, a 2-bedroom unit and a 6-bedroom unit. The 2-bedroom unit is the s orbital, the 6-bedroom unit is the p orbital, and so it can contain the second shell up to a total of 8 electrons, 2 in the s and 6 in the p. Now what determines how atoms interact with one another is the number of electrons in the outermost shell of the atom. And these electrons are known as valence electrons. Okay, and so these electrons in the outermost shell are the ones that interact with the electrons in the outermost shell of other atoms. And here in this is an electron dot diagram, and it shows different elements like hydrogen, helium, lithium, beryllium, and a different number of red dots, and those red dots are the number of electrons in their outermost shell, so the number of valence electrons. So these are the electrons that would interact with other atoms, the valence electrons of other atoms. And so when these electrons interact with one another, it results in atoms bonding together. So we rarely find atoms by themselves. Usually we find atoms bonded with one or more other atoms to form what's known as a molecule. Example of a molecule is H2O. This is simply water. So the chemical formula for H2O is hydrogen, and the subscript to the right of the chemical element is the number of atoms in the molecule. So there's 2 hydrogens in water, and if no subscript is written, that's an implied 1. That's 1 oxygen. So water has 2 hydrogens and 1 oxygen. So that is the water molecule, 2 hydrogens bonding with 1 oxygen. But why do certain elements bond with others? Well, it's because they're following this rule called the octet rule. The octet rule states that atoms like to have 8 valence electrons. They like to have 8 electrons in their outermost shell. And in order to do so, if they only have a few electrons in the outermost shell, they will give them away so that their outermost shell, the one underneath, will be then full. Or if an atom has a lot of valence electrons, and it'll just take on a couple to fill up that shell, that outermost shell. And so by giving away or taking on valence electrons, atoms share these electrons in a manner that both atoms, or all atoms interacting with each other, all have 8 valence electrons. In this process of sharing or transferring electrons from one another is called chemical bonding. And they do so that each atom has 8 valence electrons. So for example, the sodium chloride, just common table salt, is 1 sodium atom, Na, bonded with 1 chlorine atom. Sodium has 1 valence electron, chlorine has 7. So sodium, having only 1, it finds it's easier to just get rid of 1 valence electron instead of finding 7. So it gives away 1 electron. Chlorine, having 7 valence electrons, finds it easier to find and take on 1 electron than to give away 7. So sodium lends its electron to chlorine, and they bond together, in doing so forming sodium chloride. So in this case, sodium giving away an electron and chlorine taking on an electron, those atoms are no longer electrically neutral. They have a different number of protons than electrons. And any atom that is not electrically neutral is called an ion. So sodium and chlorine are considered ions. Ions like to bond with one another. There's 2 types of ions. Ions that give away electrons, like the sodium giving away its 1, are known as cations and are positively charged because they have 1 less electron than protons. And atoms that take on additional electrons and develop a negative electrical charge, a net negative electrical charge, are known as anions, like chlorine, which took on an additional electron. So cations like to bond with anions. So now that we have an idea of why atoms bond with each other to form molecules, now we're to have an understanding of, well, what atoms are present on Earth that are going to interact with one another. Well, so there's a surprisingly few, in that 98.5% of Earth's crust is composed of 8 elements. Those 8 elements and their relative abundances are listed here. We have oxygen and silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. So oxygen and silicon are the 2 most abundant elements in the Earth's crust. And so these 8 most abundant elements and the 1.5% of all other elements, they chemically bond with one another to form molecules in Earth. And these molecules, they accumulate into what are known crystals, and these crystals are known as minerals. And it is out of minerals that rocks are made. Okay, so a mineral is an aggregate of molecules formed from atoms bonding together. And to be a mineral, these 5 criteria have to be met. The substance has to be naturally occurring, has to be a solid substance, has to have an orderly crystalline structure, be generally inorganic, and needs to be able to be represented by a chemical formula. So we'll go through each one of these. So naturally occurring minerals, they form by natural geologic processes. So any material that's produced in a synthetic manner, made by people, is not a mineral. So for example, plastic and nylon, being synthetic, are not minerals. Are solid substances. Only solid crystalline substances are minerals. For example, ice is a mineral, while liquid water or water vapor are not minerals. And the only exception to this rule is mercury, which is only found in a liquid state on Earth. Mercury, even though it's liquid, is still considered to be a mineral. Orderly crystalline structure. So minerals are crystalline substances, and they are so because the atoms that compose them are arranged in an orderly, systematic manner. And this orderly packing of the atoms produces these regularly shaped objects that are known as crystals. And there are some naturally occurring solids, like volcanic glass, that are not crystalline because they do not have a crystal structure and therefore are not minerals. So not all naturally occurring solid substances are minerals. Some lack the crystalline structure. So to illustrate what we mean by crystalline structure, here is some more sodium chloride, where the green atoms are chlorine, the purple are sodium. You can see the chlorine bonds with sodium, and sodium bonds with chlorine, and there's a systematic ordering of the atoms, chlorine, sodium, in all 3 directions. And this gives us rise to this shape, which is like a cube. And so halite, which is a mineral, sodium chloride, has this cubic crystal shape. So how it breaks into these flat perpendicular surfaces. Minerals are also generally inorganic, which means that minerals are not made of organic compounds. Okay, organic compounds are hydrocarbons or carbohydrates, like sugars. So sugar, even though it is naturally occurring, it's crystalline and solid, it is not a mineral because it is organic. And finally, minerals have to be able to be represented by a chemical formula. So because minerals are crystalline, the ratio of elements in a mineral remains constant. And because of this, it can be represented by a chemical formula. So for example, the mineral quartz is composed of silicon and oxygen, SiO2. So there's 1 silicon atom and 2 oxygen atoms in quartz. That's the ratio. So if you could take a piece of quartz and break it up and separate all the silicon from oxygen, there would be twice as many twice as many oxygen atoms as silicon atoms. So the ratio of silicon to oxygen will always be 1 to 2. Same thing, for example, the mineral olivine. It has magnesium and or iron. Okay, it's either 2 magnesiums, 2 irons, or 1 of each, bonded with 1 silicon atom and 4 oxygen atoms. So the ratio of magnesium and or iron to silicon to oxygen will always be 2 to 1 to 4. Okay, and so this ability to be represented by a chemical formula is because of the crystalline structure of the mineral. So rocks are made of aggregates of minerals. So this is a piece of granite. So this is a rock commonly found in continental crust. You can see these little smaller crystals of different shape. And these different colors. And these different colored crystals are different mineral crystals. In this piece of granite, we have some quartz. Yeah, that's the clear mineral. We have some hornblende, that's the darker mineral, and some feldspar, that's the pink mineral. And so this granite is composed of several different intergrown crystals of various minerals. And so the oxygen and the silicon, they bond together to form what's called silica, SiO4. And the silica is the basic building block of rock. Okay, and minerals that contain silica are known as silicates. Minerals that do not contain silica are known as non-silicates. So silicates, they contain 2 of the most abundant elements on Earth, silicon and oxygen. And these silicon and oxygen, they bond together to form what's called the silica tetrahedra. So for example, olivine, which is the most common mineral in Earth's mantle, it has iron and or magnesium, 2 atoms of iron and or magnesium bonded to this silica tetrahedra, SiO4. And it's called a silica tetrahedra because of the shape of the molecule. So we have 1 silicon atom bonded with 4 oxygen atoms. And if you can imagine that a polygon, so each oxygen atom is a vertex or corner, and then you have the faces in between. You have a 4-faced polygon. 1, 2, the back face there is 3, and the bottom face is 4. So that's a 4-faced polygon, so that's a tetrahedra. So that's how it gets its name, the silica tetrahedra. So this molecule right here is the basic building block or the foundation of rock. So silica tetrahedras, they can share oxygens with adjacent silica tetrahedra sometimes. And so they can share no oxygens, so they can share anywhere from 0 up to all 4 of their oxygens with other tetrahedra. And the process of silica tetrahedras sharing oxygens with one another is called polymerization. And this forms different types of silicate structures whenever the silica tetrahedra polymerize. And the different types of silica structures are the result of different numbers of oxygens being shared. So the single tetrahedra structure is just isolated tetrahedra that aren't sharing any oxygens with each other, so there's no shared oxygens. The single chain structure, which is just a chain of tetrahedra bonded together, each tetrahedra shares 2 oxygens with the other tetrahedra. We have double chains, which is 2 single chains linked together. Some tetrahedra share 2, other tetrahedra share 3 oxygens. We have the sheet structure, where each tetrahedra shares 3 oxygens, and the 3-dimensional structure, where each tetrahedra shares 4 oxygens. Now this kind of seems abstract, just looking at it in text. So if we look at it in image, you can see this is the independent or the single or isolated tetrahedra, so each tetrahedra is on its own. No oxygens are being shared. Right? But then here, if you look at the single chain, you see, say, for example, let me get the pen here. this tetrahedra right here, it's sharing 1, 2 of its oxygens with adjacent tetrahedra. And if you look, each tetrahedra in this chain is sharing 2 oxygens, linking the tetrahedra together into a chain. The double chain structure, some tetrahedra are sharing 3, like this one right here. It's sharing 3 of its tetrahedra. 1, 2, 3. Or other tetrahedra only sharing 2, like this one. This one right here. It's only sharing 1, 2. But this is just 2 single chains linked together to form a double chain structure. Then there's the sheet structure, where each tetrahedra is sharing 3 oxygens. So for example, this tetrahedra right here, it's sharing 1, 2, 3 oxygens. And finally, the 3D structure is whenever all 4 of the oxygens of the tetrahedra are being shared with other tetrahedra. So these different silicate silicate structures that different minerals have, they give them different properties. Okay. And we're going to look at those properties now. First, starting with the optical properties, then the crystal shape, and then we're going to look at the mineral strength. So the optical properties of a mineral are basically how the mineral interacts with light. We have the luster, the ability to transmit light, color, and streak. First, we're going to start with luster. The luster of a mineral is how it reflects light. So minerals can reflect light you could say, poorly and be dull or earthy, or a mineral could reflect light very well and have a metallic luster. And so minerals can have greasy or resinous luster, look pearly, look glassy. Just basically how the mineral looks based upon how light is reflecting off of it is the luster. The ability to transmit light. Some minerals are opaque. Actually, most minerals are opaque. No light can pass through them. You see us looking at some of this quartz. Some minerals are translucent or even transparent, where translucent light can pass through them, but no clear image can. And transparent means the mineral is so clear, the crystal is so clear that you can see a clear image pass through the mineral crystal. Then you have the streak. The streak is the color of the mineral in a powdered form. Believe it or not, the streak of a mineral is not always the same color as the mineral itself. Now we have the crystal shape or habit. Now, different mineral crystals have different shapes. They can have bladed, banded, prismatic, or botryoidal, and or you have cubic or rhombohedral. There's all these different types of mineral crystal shapes that are the result of how the molecules are compacting themselves into the crystals. Then we have the mineral strength. And so there's 3 different ways in which mineral strength is measured. There's the tenacity, that's the mineral's resistance to breaking or to forming. The hardness, measure of the resistance of a mineral to scratching or abrasion. Then there's also the cleavage. Cleavage of when a mineral has cleavage, that means that some atomic bonds in the crystalline structure are weaker than others. And minerals will tend to break along planes where those bonds exist. So the mineral will cleave along these planes. And first we're going to take a look at hardness. So the hardness of a mineral is a measure of the mineral's resistance to scratching or abrasion. And geologists use Mohs scale of relative hardness to basically help assess the hardness of a mineral. So what Mohs scale of relative hardness is there's 10 index minerals: talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, and diamond. And they're ranked 1 through 10, each one having a different hardness or a different amount of resistance to being scratched. And here are some normal day materials and their corresponding hardness on the Mohs scale of relative hardness. So for example, a fingernail ranks at a 2.5 on the Mohs scale of hardness, What that means is a fingernail is harder than gypsum but softer than calcite. So you could scratch and abrase gypsum with your fingernail, but you would not be able to scratch calcite with your fingernail. In fact, calcite would scratch or abrase your fingernail. All right, and so, for example, a piece of glass, you would be able to scratch a piece of glass with orthoclase, but you would not be able to scratch glass with anything else down here. Okay. Then the mineral strength, looking at the cleavage, and as I mentioned, cleavage is never, if a mineral has it, it will preferentially break along certain planes where the atomic bonds in the mineral crystal lattice are weaker. This cleavage can be very pronounced in some minerals and a little more subtle in others. So for example, this mineral, this is muscovite. It has this very clear one plane of cleavage where it cleaves into these thin sheets. And this is because muscovite has the sheet structure, the silicate sheet structure, where all these silicate tetrahedra are sharing 3 oxygens with one another to form these sheets. So the bonds within the sheet are very strong, but the bonds between the sheets are much weaker, and so those bonds can break fairly easily, and so this mineral can be literally peeled off in these little layers or flakes. And so there are many different types of cleavages. A mineral that has one plane of cleavage, it takes the shape of these flat sheets. Okay, and this is what it kind of looks like, and my sample is muscovite. Minerals could have 2 planes of cleavage that intersect at 90 degrees. So this forms this elongated rectangular prism. And so you can see this surface is rough, this surface is rough. That's not a plane of cleavage. This smooth top surface and this smooth side surface are the cleavage planes, and those planes are illustrated here. So the mineral cleaves along those planes. It breaks along these smooth sides. Okay, an example here is feldspar. Then we have 2 planes of cleavage that do not intersect at 90 degrees. Like this one here, you can see the planes of cleavage intersecting but not at 90. Then we have 3 planes of cleavage that intersect at 90-degree angles. And that forms a cubic crystal like halite. Or you have 3 planes of cleavage that do not intersect at 90 degrees. That forms a rhombohedron mineral crystal shape, like calcite here. And then you could have 4 planes of cleavage, which forms this octahedron shape. An example is fluorite. So it's amazing that fluorite actually breaks into these shapes. That's not cut like that way, like this. It actually breaks into pieces that look like that. So now we're going to look at some common silicate minerals. Okay, and if we look, the different silicate structures, like the isolated single tetrahedra, single chain, double chain sheets, and 3D framework, they result in different types of cleavage. So the isolated tetrahedra has no cleavage. The single chain structures has 2 planes of cleavage at 90. The double chains has 2 planes not at 90, at 60 and 20. Then the sheet structure has 1 plane of cleavage. And the 3D structure, it can have 2 planes of cleavage at 90 or also none in the case of quartz. So these different silicate structures result in different types of cleavages among these minerals. So looking at the 2 groups of silicate minerals, the first group is the non-ferromagnesian silicates, also known as the light silicates. These are the silicate minerals that contain relatively small amounts of iron and magnesium, basically no iron and magnesium. And because of this, they're generally light in color. That's how they get the term light silicates. So the feldspar group is the most common non-ferromagnesian silicate. All feldspars have 2 planes of cleavage at or near 90. They're relatively hard, 6 on the Mohs scale of hardness, and have a luster that ranges from glassy to pearly. There's two types of feldspar: potassium feldspar, which is also called orthoclase, and plagioclase feldspar, also known as albite. And you can see both feldspars have aluminum and silica. Potassium feldspar has this potassium bonded with the aluminum silica, but plagioclase feldspar has either calcium or sodium that bonds with the aluminum and the silica. So that's the difference between the two. And potassium feldspar, the potassium gives it a pink color, and plagioclase feldspar, the calcium or sodium, they give it a white color. Okay. So you'll notice that there's no iron or magnesium in these silicates, making them non-ferromagnesian silicates. And here's a picture of plagioclase feldspar, the one with the calcium or sodium, giving it that whitish color. Next, another common non-ferromagnesian silicate is quartz. Quartz is pure silica. It's the only mineral that consists entirely of silica and oxygen. Quartz is very hard because it has a three-dimensional silicate structure where all four oxygens are being shared.